Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today. As you step into my virtual classroom, we are officially now going to start that solving systems of equations unit. This one's going to be based on graphing scenarios here. So I have, I believe, 13 practice problems to do. 12 of them are graphs. The first one is kind of just a prelim going into it, understanding what the systems of equation things mean. If you've learned anything about them, that'd be great. I'll teach things along the way as I do a problem, but I might not really build up a problem prior to and teach the stuff beforehand, if that makes sense. I like to dive into these practice problems straightforward and say what I can say about them. If the problems become a little too redundant, I'm going to still do them, but I'm going to make sure that I teach less as I go and just go through the ropes of them. Okay? I like to make videos as hefty with knowledge and information and things for you to acquire as possible, but at some point it's overkill. So without further ado, let's go ahead and get started. My first question, number one, is the following statement correct, and explain? I'll go ahead and make a typing statement out of this one as well. A system of two equations has no solution if the graphs of the two equations are coincident lines. Now, first things first, a system of equations just means multiple equations that are arranged together in order to make something happen, whether it's solutions or anything else. Sorry, I'm clearing my path right now on my desk so I can be ready to type something in a second here. So as I'm going to get ready to type and say something about this, when two things, let's say blah, 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 when two things are coincident, what that means is they are hitting each other everywhere you go. So let's say I have this graph here that's in blue that looks like that. I'm going to make it a little bit bolder here. And then I have another one that's in green right here, but it's like the exact same graph. It's hitting everywhere that blue is. It's like, what a coincidence, we're here together, green and blue. You might not be able to see both together there, but I assure you they are there. Maybe we can do red. There we go. Can you see red with blue? So to be coincident, what it means is they're hitting everywhere at the same time. Now, to be a solution to a system of equations, you have to have a point of intersection on that graph. The question is, do these 2 points never intersect? That's what they're asking. If it has no solution, that means they never intersect. Do these 2 points intersect? Oh, yeah. They intersect everywhere. They intersect here, and here, and here, and here, and everywhere on the line. So to answer this question, a system of equations has no solution. The graphs of two equations are coincident. No, that's not correct. These two equations being coincident lines means they are intersecting. Don't worry, I'll change the formatting here. It's going to overlap. They're intersecting everywhere together, which means, let's see, together, which means they actually, in fact, have an infinite set of solutions. So that's what it means to have an infinite set of solutions, that they're intersecting everywhere together. Lines can only do one of three things. They can either intersect together once, not at all, or an infinite number of times. Now, what does it look like for something to have no solution? It would look like this. Two lines that are parallel, all right? Two lines that are parallel. So coincident lines exist everywhere together. These two happen to just, these two aren't coincident. They are parallel. That's the only other word I can think of. What does it mean for something to intersect only once? Well, it would look something like this. Two lines with different slopes like that. So we're going to run into a bunch of different ones here. We'll see what they look like. These ones do have an infinite number of solutions, though, as they are coincident. All right. All right, number two, solve the system of linear equations by graphing. Check your answer. Oh, so, excuse me, 2 through, I think, 13. Numbers 2 through 13. I don't know if we go all the way to 13. I might only go up to, let's see. Yeah, 2 through 13. The next, I can't count. The next 12 problems I do are all going to be graphing. So the same instructions come up here. When they say check your answer, you'll see what that means, but I'm going to substitute my XY coordinate pairs into the equations and see if they happen to pan out the way that I expect them to based on what I graphed here. So I'm going to try my best to graph them in the apparent form that they seem best suited to graph in. What I mean by that is I want to try and graph as many as possible in slope-intercept form and standard form. If one is already written in slope-intercept form, I'm likely going to keep it. There may be some exceptions, and I'll show you when they are and why if they exist. Otherwise, I'll keep in standard form, again, unless I need a reason to kind of graph in slope-intercept form. If they are not yet presented in either form, I will go to the one that's fastest, easiest, closest, or best, or whatever. But rewriting the equations and avoiding making tables is kind of the best approach to making these things happen. So solving by graphing, again, does mean that we graph the lines, but furthermore, we seek out the point or points of intersection, if any. So let's go ahead and get started. Number 2, y equals 2x minus 4. At this point, I'm making the assumption that you know how to graph using slope-intercept form right here. I start at a y-intercept of -4, and what I'm doing right now is plotting a bunch of points where I rise 2 and I run 1. That is up 2 over 1. That's what that point is doing here. Like I said, when it comes to teaching this stuff, I already taught this stuff before. The new stuff is systems, which means graphing both of them together, seeking the point or points of intersection, if any, and deciding what that means as far as your system goes. This is old stuff. 2x minus 4 is right there. X plus 2y equals 12. I have an x-intercept. If I hide y, my x-intercept is 12. See, this one's off the graph. This is one of those things where maybe I rewrite it in slope-intercept form if I have to, because this is off the graph here. That might be troublesome. My y-intercept, if I hide x, 2y equals 12. That means y equals 6. 1, 2, 3, 4, 5, 6. Now, 2 points make a line, so I can go ahead and just draw the line from here if I want to. The tricky part about standard form is that you have to make sure that you definitely have a ruler for this one. And it looks like I know where I'm going to be finding the point of intersection here if I graph this correctly. I'm going to go ahead and double check it after. I'm going to go ahead and double check my own solution right here. And if my double check gives me a wrong answer, I'm going to go ahead back and do this one in slope-intercept form afterward. If not, I'm good. All right, so I graphed both of my lines here. The question now becomes, and this is interesting, these lines are actually perpendicular. They make a right angle. The question is, what is the solution to the system? And furthermore, how do I know? How can I double check it? So this point of intersection is at 1, 2, 3, 4, comma 1, 2, 3, 4. This is at 4, comma 4 here. That x and that y is a solution to both equations in the system. So just to make sure that you're totally understanding this, the blue line and the green line that I drew are for 2 separate equations here. Let's actually color code these. This was blue, this was green. The blue and green lines that I drew represent the solutions for their respective equations. This blue dot for the blue equation, every single point that I plotted plus the line itself represents an infinite number of x, y values that I could plot into here and make the statement true. Like, check out this point, 0, -4. 0 equals 2 times, no, hang on a second, I said that wrong. -4 equals 2 times 0 minus 4. Yeah, -4 equals -4. So 0, -4 works in the blue equation. But if I substitute 0 for x and -4 for y into here, I get a statement that says -8 equals 12. And -8 doesn't equal 12 because 0, -4 is not a solution to the green equation. It's not a solution to it. The only ones that are solutions to the green equation are these guys here. Any of these points, including 12, 0, including 0, 6, including what looks like maybe, I don't really know any other ones. Maybe this point right here. I don't know. But it looks like 4, 4 is also a solution to that system. But it looks like it's also a solution to blue. When they say check your answer, what they're asking you to do is check and see if I can substitute 4, 4 into both equations and get a true statement out of both equations. If it satisfies only one, that is not good enough. It must satisfy both. Are we at halftime? We must be at halftime. I haven't seen football action in a while. All right, let's check it out. Start with this equation here. 4, good thing they're both 4s. 4 equals 2 times 4 minus 4. So I get 4 equals 8 minus 4, or 4 equals 4. So the first one checks out here. The second equation, 4 plus 2 times 4 equals 12, which is 4 plus 8 equals 12, or 12 equals 12. And that seems to check out as well. So yes, this one right here is the solution to the system. I leave it as an ordered pair. I don't write x equals 4, y equals 4. I need to know that it's specifically x equals 4 when y equals 4. It's this ordered pair 4, 4. And that's the answer to number 2, and it's done by means of that graph. Okay, not every other problem is going to be as long as that. That's the full bore explanation of what I was doing and why. I don't hope to land on a wrong answer at any point during teaching this, but if I ever do, the double checking will be a good way of showing that, and that's a good reason why you might want to double check. Okay, number 3. I'm going to go ahead and I'll graph all these in blue and green if I remember to do that. Number 3, y equals negative 1/3 x plus 2. All right, that one's already in slope-intercept form, so let's go ahead and get started on that one. I got to scroll down a little bit, though, because my head gets in the way of this thing, and I don't really know what to do about that otherwise. Y equals negative 1/3 x plus 2. I start at 0, 2. Okay, and then I'm going to go negative 1/3 is going down 1, right 3, something like that, plotting that point. And negative 1/3 x, I think you remember that. So down 1 over 3, down 1 over 3, etc. If I go up 1, left 3, I'm kind of continuing that same idea of that path. So let's keep going. Oh, look, it's not halftime. There's still football going on. Got to check that score in a bit, huh? Here we go. All right, so this is y equals negative 1/3 x plus 2. There is the graph. I'm not done, of course. I still need to graph the green one. And furthermore, I would then need to check it out and see if all was working. This one right here, there is another way I could do this. I'll show you it afterward, because I talked about standard form and slope-intercept form, but there is another form I could be using with this. I'll get to it later. This green equation here, y plus 4 equals negative 4/3 x, not quite yet in either of those previous forms that I mentioned, but it's very close. It's very close to slope-intercept form. If I go ahead and subtract 4 from both sides right here, I get y equals negative 4/3 x minus 4. So there's my equation there in slope-intercept form. I'm going to go ahead and graph that one, if I can still see it. There's a 0, negative 4 is where I'm going to hit right here. Negative 4/3 x, negative 4/3 is my slope, meaning down 4, 1, 2, 3, 4, and right 3, plotting a point. But it's kind of important for me to go up and to the left, because I need to find out where these two intersect, right? So I got to keep going up and figure out where that goes. Up 4 over 3, up 4 over 3 right here. The kind of nice thing about these ones, if they ask you to solve by graphing, it's likely you're not approximating, but instead you're landing right on a crosshair of integers right here. So which means I already know my answer based on these two plotting in the same spot, but they also still want me to fully graph it, which is, it's common courtesy. So I'm going to go ahead and do that right now. Draw that line. And again, clearly the point of intersection was already established through the points that I drew here, but right here you can see there is that point of intersection, which becomes 1, 2, 3, 4, 5, negative 6, negative, let me do that again, negative 6, comma, 1, 2, 3, 4, 4. All right, so let's double check those two. This one, and look, it's practice with fractions. You got to be able to practice with fractions as needed, or you got to find other means to do this, and maybe in one of these problems later I will show you another way to not deal with the fractions. But you would still be doing something to the fractions to not deal with them. You're basically going to bust the fractions. Okay, 4 for y. 4 equals negative 1/3 times 6 plus 2. 4 equals... Now, if I ask you what 1/3 of 6 is, you might likely know that answer. But if I asked you what 1/7 of 84 was, you might not know that answer, unless you know how to deal with these things. Essentially, what's happening is 1 is multiplying with 6, and together those numbers divide by 3. Remember, 6 doesn't multiply with the 3. 6 is in the numerator, and 6's denominator is essentially a 1. 3 multiplies with 1. Oh, by the way, this whole number is negative, too. 1 times 6 is 6, divided by 3 is 2. 1/3 of 6 is 2. Therefore, this number that I'm looking for is at negative 2. Negative 2 plus 2 does not seem to equal... You know what? It doesn't seem to equal That's 4 equals 0. Did I do something wrong? Yeah, I did something wrong. My answer's not wrong. Problem is I didn't substitute negative 6. So there we go. That was not intentional. Negative 6 times negative 1/3 is a positive 2. Now 2 plus 2 is 4. So that's a thing where, that doesn't happen very often, where when you double check an answer, the whole point is that in your double checking, all that math is supposed to be correct. And then when you get incorrect calculation, you say my answer's wrong. Problem was I had an incorrect calculation, even though my answer was right. So I had to change my double checking. That would suck if your double checking actually stirred you into a wrong answer. You do not want that. You do not want that. So let that be a lesson to you guys. Don't just ignore your negatives. Okay, so let's look at the original equation on this one here. And again, I want to look at the original one to know that I solved the system correctly. Because look, I could have done incorrect work right here. I don't want to just plug it into this because I graphed based on this. I want to see the original equation and see that I substitute -6 and +4 here. See if that works. 4 for y. 4 is going in for y, plus 4 equals -4/3. Let's try that again. 4 plus 4 equals -4/3 times -6. 4 plus 4 is 8. -4/3 of -6. Well, negative times a negative is a positive, so just remember that part. 4 times 6 is 24. 24 divided by 3 is 8. So we do get 8 equals 8 right there. That one pans out as well. So it looks like that one too is a correct answer. All right, so we got those two sets of solutions right there. I'm going to do one more thing with number 3 and talk about the graph of the green right here and say something else you could have done if you understand how this is kind of presented in another form. Oh, you know what? Actually, I won't do it here because, you know why? It's going to lead me to the same point. You know what I was going to do was use what's called point slope form. But it would lead me back to the y-intercept of -4, so it's never mind. We're good. All right, let's go ahead and move on. Numbers 4 and 5, same deal. No different. Y equals -x minus 6 and y equals x. Okay, it's funny how when you're presented with less information, people tend to psych themselves out even more with these kinds of problems. Don't make this harder than it seems. Just make sense of what they're asking you to do. If there are implied numbers, use them as well. Let's go ahead and take a look at what we got here. Y equals -x minus 6 also means y equals negative, that's too dark a blue, also means y equals -1x minus 6, or -1/1x minus 6. See, the time that we actually like fraction is with slopes because we like how much we're rising and running. So actually, we prefer fractions in these cases here. Down 1/1, starting from -6, let's go ahead and do that. Starting from -6, let's go down 1/1, over and over. Clearly, this will be a whole bunch of points I'm going to plot. So just talking through this one, again, makes sense that you understand there is a coefficient of -1 in front of x if all it says there is just -x. So it looks just like this. And I'm going to go ahead and connect the dots. By the way, I didn't state this before because I'm not drawing the arrows myself, so make sure you draw arrows at the end of your lines here when you do this. You got to just state that that line is going on forever, indeed. Y equals x. Again, don't psych yourself out too much here. If you want to write it in slope-intercept form, that is a 1x in front, or 1/1x. And what's the y-intercept? Don't say nothing. It's 0. 0 isn't nothing. 0 is the y-intercept. It's also the x-intercept. It's crossing right through the origin right there. And I go up 1/1. That's what a slope of 1 is going to tell me. Up 1/1, plot my points. Clearly, I'm going the wrong direction as far as intersecting my two lines here, but you know what? There's nothing wrong with just getting the idea of get as precise as possible. Understand what up 1/1 means. In this case, down 1, left 1. As I get these, this hits the entire both set of corners. Go ahead and connect my dots there. And you can, again, at one point, I clearly hit the point of intersection. It's right there. None of these problems are going to change. So it's clearly, you can see that I'm hitting that sense of redundancy for you already. If you think this is a little too much and you want to move on along, you're good. So if you're understanding this stuff, great. Left 3, down 3. That's at -3, -3 as the point of intersection. And double check. Let's do this mentally this time. Let's start with the first one, or the second one. Does -3 equal -3? Yep. So that one's good. And actually, you know what? That's going to lead me to a point for what else you could kind of done with y equals x if you were really confused. The other one, -3 equals the opposite of -3. That becomes 3 minus 6. Yeah, -3 is 3 minus 6 indeed. So that one works out too. So -3 is your answer. All right. If you had trouble graphing this green one still with understanding slope and y-intercept that I did right here, look at this. It says y equals x. That means no matter what your x value is, your y is the same thing. What happens when x is 5? Y is going to be 5. That's why there's a point right here that's 5, 5. What happens when x is -2? Y is going to be -2. That's this one right here. So it's a clear just whatever x is y is kind of deal. All right, that's all there is to it. There's nothing else there. So pretty simple one that people end up overthinking because, hey, it's not in slope-intercept form, even though it actually is. All right, number 5, y equals 4/3 x minus 4 and y equals 4. Start with the first one, very straightforward. This looks a lot like number 3's first question, the negative 4/3 x, only this time it's positive. I'm going to go ahead. It's a minus 4 to start with. Now we're going to go up 4 and right 3. Let's draw this graph for you. And looking like pretty good right there. Use your ruler, of course. Get as many points as possible on that thing as you can. Connect the dots. You're hunky-dory. All right. That's the first one there. That checks out. Second one is in green here, y equals 4. And in this one, again, if you want to write it in slope-intercept form, the x term is missing because it's multiplying by 0. That means you have a slope of 0 in this thing, which means you don't rise at all as you run forever. So it's going to be a flat horizontal line starting with a y-intercept of positive 4. What does that mean? It means the line goes across straight and flat like that. That's y equals 4 right there. And yes, this is y equals 4. Everything here is something comma 4. This is negative 9 comma 4, 0 comma 4, and the important one here is 6 comma 4. So the point of intersection right here is 6 comma 4. Not a minus. Let's try that again. 6 comma 4. Okay. Let's check that out. Substitute 6 in for x and 4 for y in the bottom equation. There is no x. Well, there is right here if you want to do that, but guess what? 6 times 0 is 0. It's kind of nothing to substitute other than 4. 4 equals 4. Of course that one checks out. That one works for sure. 4/3 of 6. We established that last time. That number was 8. 8 minus 4 equals, plug in 4 for y, 4. It looks like that one checks out too. 6 comma 4 is your solution to that system, done by graphing as well. Excuse me. So we're learning how to solve systems by graphing. Just want to make sure you're understanding that. We are graphing to solve the system. If we see the point of intersection, that means there is that solution that we find. All of these so far has just had one solution. I don't know when we hit the no solution cases, infinite number of solution cases, but keep in mind, as we've seen these so far, they've all only had one solution. And that is likely the case of a lot of linear equations here. Give me a second. I got an important phone call. I'll just pause my video once. All right, sorry about that. Okay. Excuse me. We finished 4. Okay, we finished 4 and 5. Sorry, I'm on the screen. I'm off the screen. All that. Okay, let's go ahead and keep moving on here. Number 6, number 7. All right, y equals negative 2x plus 2. I used blue for the top one, right? 2 is where we start, and negative 2x going down 2 over 1. All right. Like I said, eventually, hopefully, we hit some no solution, infinite number of solutions problems. I don't think that's showing up in this one just yet. But we'll find the point of intersection. We'll double check. If the problem is good enough that we can double check mentally, I'll go ahead and just do that. I don't have to write each one for you. Your double check is your business, so we'll see. You want to take my word for it that it's correct, but I think we can do these ones mentally if there are no fractions. Y plus 2 equals 2x. If we subtract 2 from both sides, it becomes y equals 2x minus 2. It looks quite like this equation. Both of them have 2's, but both of the signs are also opposite of each other. Especially the more important one, especially the slope. If the slope is opposite sign, that just means, hey, it's a different slope. So I start at negative 2, and then I go up 2 over 1. You can already see what it looks like the answer is going to be, which is 1 comma 0. But I must satisfy their request at actually graphing this. Let's get a lot of points in here, draw the lines, see that point of intersection is 1, 0, and double check and make sure everything is good. Mr. Robinson, you talk a lot. Yeah, I do. I'm filling the air when I am drawing this thing. You try and do the same. All right. I got 1 comma 0 as my solution here. 1 for x, 0 for y. Let's check it out. Again, do the original equations. 0 equals negative 2 times 1 is negative 2 plus 2. Yep, 0 is negative 2 plus 2. That's good. 0 plus 2 equals 2 times 1. 2 equals 2. That one's good. 1 comma 0. I like it. All right, here we go. Y equals 1/2 x plus 5. Okay. Blue, let's go and do that. Start at 0, 5. I'll rise 1, run 2 for you. All right. And let's go backwards here. The next problem I'm going to do, you can do it in slope-intercept form. Likely I would encourage it in a lot of different instances. For this particular problem, just to be different with it, I'll show you standard form for it. All right. Want you to see what that one looks like. I might not get a good looking, we'll see actually. I think actually they might be fun. I might get a fraction intercept somewhere. So we'll see if this pans out the way I want it to. But let's go ahead and do the green with a different style just because I want to. I get bored of slope-intercept form sometimes. How do I get this in standard form? 'Cause it's kind of in standard form. You're looking at this right now. You're like, it is. The x and y on the same side of the equation. Standard form also kind of has the non-fraction information. So I have a fraction right here of 2/3. I want to get rid of it. So it's dividing by 3. If I go ahead and I multiply everything by 3, that means both sides right here, times 3 times 3. I'm going to go ahead and get 3 times -2, which is -6. 3 times y, which is 3y. And 3 times 2/3, that 3 divides by 3 and they cancel and you're left with 2x. So I get 2x plus 3y equals -6. All right, that's standard form for you right there. That's standard form. All right, x and y intercept. X-intercept set y equal to 0. Hide, 2x equals -6. And divide, we get x equals -3. That's my x-intercept. I'm going to go ahead and plot that point for you right here. Good, it was not a fraction x-intercept, I'm glad. And the y-intercept, 3y equals -6, so y equals -2. Hide and divide, y equals -2. Go ahead and plot that point. And now, 2 points make a line. Let's go ahead and graph it. It looks safe to say that it's going to cross at this one particular point you're going to see here in a second. Just got to eyeball this. Hey, not bad. So it looks like it's hitting right at this point right here where they cross, which is that integer set -6, 2, I think. And if I didn't count that right, we'll see it in the double checking. Now, when I double check again, I do have to use the original equation. Sorry, I can't use the standard form one because something could have gone wrong here to get me that answer. Remember that. So let's go ahead and check this. -6 for x, 2 for y. 2 equals 1/2 of -6 plus 5. Half of -6 equals -3. -3 plus 5 equals 2. So 2 equals 2. The first equation checks out. All right, the second equation, give me some room over here. I'm going to take 2/3 this time of -6. We're going to do plus 2 equals -2. Let's check it out. 2/3 of -6 is, it's -4. 2/3 of 6 is 4. 2 times 6 is 12, divided by 3 is 4. So this is -4 right here. Whoops, -4 plus 2 equals -2. You betcha. -2 equals -2. That one checks out. So this is the correct answer there for number 7. 8, 9, 10, 11, 12, 13. All right, I got 6 more problems to do. I feel like I'm going kind of slow with these. So anything else that's kind of the same, where the points of intersection, ooh, this problem's different, where the points are kind of same-ish, they've seen the same what we've done before, let's just mosey on over and see what we got to do. If something's different, like no solution, infinite number, I'll stop you. Number 8, y equals 1/2 x minus 2. Was that the, did we just, no, it's different. Y equals 1/2 x minus 2. There was 2x minus 2 and 1/2 x plus 5. So here's the first graph, 1/2 x minus 2. All right. Hold on. Almost. All right. You might be asking yourself right now, Mr. Robinson, is there a way to solve these systems of equations without graphing? Yes, that's for future units. That's for the substitution unit and the elimination unit. There is a way that you can understand your solution if there is no solution, or if there's an infinite set of solutions, but we'll have to wait until we run into a problem like that. We could do standard form or slope-intercept form, I guess, because I have to move this thing over anyway. We might as well just add these two numbers over, plus 3 to both sides, and then let's go plus 1/2 x to both sides, and then we're going to get, whoops, hang on a second, plus 1/2 x to both sides. Remember, these do not combine. These cancel out on this side. We get y equals 1/2 x plus 3. Oh, okay. All right, trickery stuff here. Y equals 1/2 x plus 3. I got to graph this one, and I will. But before I do, I want you to pay close attention to both equations that you're looking at right here. 1, 2. These are both in slope-intercept form, which means my coefficient in front of x is indeed the slope. The slope is 1/2 for both of these. Same slope, that means they run in the same direction. Things that run in the same direction means that they have potential to be parallel because of this kind of action here. The only thing that would make them not parallel is if, just like problem number 1, if the two lines were coincident, meaning they cross the same point everywhere. And one way to see that in your equation form is at the y-intercepts. If the y-intercepts are the same, then the slope, then the lines are parallel. If the y-intercepts are different, let me say that again. If the y-intercepts are the same, the lines are identical. If the y-intercepts are different, like these two, then the lines are parallel. They'll never touch each other. And let's go ahead and take a look at that. I'm going to go ahead and graph these, graph the green now. 1/2 x plus 3. I'm going to go up right here. Let's go rise 1, run 2, etc. Rise 1, run 2. Now, I'll let you know clearly it's possible, although probably not likely, that a textbook or a math teacher or somebody could ask you a question about solving something by graphing, and the 2 points are like they would intersect eventually off the grid, but you just can't fit them on the grid to find the point of intersection. That's possible. I'm going to say it's highly unlikely. But just because you don't see two lines intersect on the grid doesn't mean they don't intersect ever. So as you look at this problem right here, that's great. What if the line instead looked like this? Right? And off the grid they're going to intersect eventually, but you don't see it right now. What? Because they don't intersect right now, you say no solution? No, these two lines are going to intersect. Look, if I just keep increasing this one like that and this one like that, eventually they cross way over here. But so that's why you have to know either number 1, what does it look like for lines to be parallel? Okay. Or number 2, how do I know the lines are parallel? And I know the lines are parallel because the slopes are the same. Obviously, they look like they're parallel. I set up 1/2. These lines are never going to intersect. As they go on forever, they will run the same direction the rest of the way, even as they go on forever. These will never intersect, and lines that do not intersect means there is no solution. No solution means there is no single xy pair that I can substitute in both equations at the same time and get a true statement for both. Yes, this has its own set of true statements. Yes, this has its own set of true statements. None of them have a single xy coordinate pair in any case whatsoever that makes both equations true at the same time. It is impossible. There is no solution to this problem. I'm glad we ran into one of those. All right, number 9, I'll go straight up on the form that they have here, but I'll let you know what. If you do slope-intercept form more often than not, then you'll be pretty privy as to see whether or not the equations have the same slope and y-intercept. So you want to convert slope-intercept form the rest of the way, be my guest. It's up to you. Standard form does have its uses, though. And first, I'm going to graph out of it. And then if slope-intercept form tells me more about what I want to do, then I will. All right, so y equals 2x plus 4. That's the basic blue right here. Starting at 4. Let's go up 2/1. All right. This will be... If you're not feeling out these graphs just yet, you got to do a lot of practice on them. Not saying like then you can't understand it. I'm saying you'll have to. Like if I'm going too fast for you with it, there are other ways to learn it. I've taught other videos with it, the practice of it. So definitely feel that one out. All right, this one, x and y-intercept. Let's do this mentally. X-intercept set y equal to 0, negative 4x equals 8. So x equals negative 2. So right here. Oh, already crossing at the same point. Look, there's a solution. 2y equals 8, so y equals 4 right here. Okay. 2 points make a line. And it looks like they make the same line as we're looking at right now. So I'm going to make a thinner green line. You probably can't see it very well, but I promise you it's there. If you want me to do red again this time, I'm fine doing that. Let's do red. There's the red line. Oh, I made the wrong one red. There we go, like that. Okay. They are the same line, just like answering question number 1. These two lines are what's called coincident. They intersect everywhere. This is called a dependent system where there's an infinite number of solutions. Everywhere that one equation is a solution, the other equation is also a solution. everywhere. At 2, 8, at 0, 4, at negative 2, 0, at negative 5, negative 6. All of these are solutions for both equations at the same time. Double checking might have to happen still. Like, how can you double check? Maybe you have to check a couple of bullet points that work for both. Which ones did I say? Like 2, 8. Let's go ahead and check one out. 2, 8 right here would be a solution. It's not the only one, but it would be a solution here. 2 for x, 4, 2 times 2 is 4, plus 4 is 8. So that one works. Negative 8 plus 8, let me say that again. Negative 8 plus 16 equals 8. That one works as well. So 2, 8 works. Let's try negative 5, negative 6. You know, you might want to check more than one here. Negative 5, negative 10 plus 4 is negative 6, and 20 minus 12 equals 8. So that one works as well. So you don't list these solutions there. Instead, all we say is infinite number of solutions. Let me erase those two. Infinite number of solutions. That is how we say that answer. That is totally fine. And that's all it's saying. Again, this is what's called a dependent system. The one answer ones are called an independent system. And then the no solution ones are called an inconsistent system. This is very consistent, as you can tell. All right, numbers 10 and 11. You know, something interesting I want to try and do with number 11 to show you. Oh, you know what? Here, let me go back for 1 second. So for this one here, if I rewrote it in slope-intercept form, notice what happens. And really, what do you expect to happen? If I add 4x to both sides, I get 2y equals 4x plus 8. And if I divide by 2, I get y equals 2x plus 4. So look what I already kind of know the answer to before I even graph them. They're both y equals 2x plus 4. That means they're the exact same line. See, it's not just enough to have two lines that are parallel to say that they are, it's not enough to have two lines have the same slope to say that they are parallel. You need to know that they have different y-intercepts, call them parallel. If they have the same y-intercept, guess what? They're the same line, just like this one is. So going with number 10 here, we could get y by, let's try slope-intercept form here. See if we can kind of go straight from there and then make our graph. Subtract 12x from both sides. I get 4y equals negative 12x plus 4. And I divide everything by 4. I get y equals negative 3x plus 1. Again, subtracted 12x and then divided by 4. Y equals negative 3x plus 1, just like the equation above. These are already the same one. I already know that my answer is infinite number of solutions, just like the last one. And, it's enough to just graph one of them at this point. So let's go ahead and do that and work on a merry way. I'm well past a half hour. I wanted to get this one done yesterday. So here we go. Y equals negative 3x plus 1. Both of them are the same thing. They intersect everywhere together along this line. So it is this single line that I graph and draw, and I am set with an infinite number of solutions. And, the way that I work that out, it's kind of peachy. It's good because I rewrote this for the sake of graphing it anyway. Okay. Number 11, y equals 4x plus 4, and then this one right here, or y equals 4x plus 4, and then this one right here, again, slope-intercept form. You want to do this one slope-intercept form again? Why not? Speed up time these days here. Not plus 4 right here. Hold on. Plus 4x, and then minus 4 minus 4. Remember, I got to move that thing over in a different way. All right, so now I'm going to get y equals 4x minus 4. Y equals 4x minus 4. Same slope. These both have 4s too as well, but notice one is positive, one is negative. These are not the same y-intercept. I do got to graph them. They will be different graphs. So the first one right here, y equals 4x plus 4. I start at here. I go up 4 over 1, plot the point, etc. Keep moving along. And then the other one's going to be y equals 4x minus 4. So I'm starting at a different spot, despite the fact that I have the same slope there. It is going to be a different spot that I start in, so it is going to change the nature. They aren't going to intersect. Same slope, different y-intercept. Let's check it out. 4x minus 4, now I'm going to start right here. I'm going to go up 4, right 1, over, and over again. So clearly, same slope, they go in the same direction, but but they do not intersect. Much like that one that we saw before, never intersecting, no solution. No solution. There's nothing I can substitute in one that can help me with the other. That is no solution. Okay, parallel lines, no solution. Single line, one on top of the other, independent, infinite number of solutions. Excuse me. All right, last two numbers, 12 and 13 here. 12 has a bit of a rough case here. We have a y-intercept of 1/4, and I personally, alongside anyone else, do not love using fractions for y-intercepts. 1/4 is about right there. That means I'd have to rise and run 1 on a fraction. I don't want to do that. There's no avoiding it in some capacity, but I'd rather go for only having to point as few points as possible. To plot as few points as possible. So for me, that means going into standard form. I'll go into standard form, find the x and y intercepts, and then kind of be done with it. So for this one here, I got a few things I got to do. Number one, as these both divide by 4, I got to multiply everything by 4 to start. So multiply by 4, I'm going to get 4y equals, see, in multiplying these by 4, the 4 cancels these 4's down here. So I have negative 3x plus 1. If I add 3x over, I get 3x plus 4y equals 1. Okay, so that's my standard form equation. The x-intercept, this isn't great regardless. These are small fractions. You know what I might do is I might change the scaling on this thing here. I get an x-intercept here of 1/3. I'm going to take, hide and divide by 3. And then I'm going to get a y-intercept of 1/4. I think we already saw that before, of 1/4. Okay, so these are pretty small. I'm not going to change the scaling. Let's just go with it. X-intercept of 1/3 is about ish. And you know what? If I'm wrong with my answer, I'm wrong because this isn't perfect scaling right here. 2 points may make a line, but the closer the 2 points are, the less precision you have venturing out this way. So we'll see. I might have some struggles with this one. You might have some struggles with this one. It might not be an easy one to get across. This one here, if I add the 2 and subtract the 3/4 x, I get y equals negative 3/4 x plus 2. Because it's an integer y-intercept, I'm good just graphing that one kind of as advertised. So I'm going to go down 3 and right 4. Notice I didn't draw the line at the other one yet. I'm going to make a guess at where it's supposed to be hitting after I see these things after I see the green one be graphed. Okay, so I'm going to first graph this green one. Then I'll draw the blue alongside it and say, this is my guess. And it's one, even for me, even for Mr. Robinson, it's one that I'm going to have to double check. I won't be able to guarantee that my answer is correct. There's my green one. Green one's fine. Blue one's the question. So in this blue one here, notice how, I don't know. Are these, oh, I should have seen this from the beginning. These are parallel, so these won't intersect. I was going to try and force an intersection here. You know what? Maybe it was better to just leave this like this. I have to graph it still, but maybe it was better to leave this like this because negative 3/4, negative 3/4. I'm talking myself out of doing a strategy here. But no, you know what? That was good to look at because at least I can just draw the line simply. I don't have to plot a bunch of points. I'm good with those. All right, so I'm not done. I still got to say what? No solution. Looks like they buried the no solutions and infinite number solutions way back here at the end. All right, last one. Let's see if I can see if we can make sense of it just by kind of getting this in slope-intercept form like before. Add 5x, subtract 4, y equals 5x minus 1, y equals 5x minus 1. You know what that one's going to be. 5x minus 1, 5x minus 1, infinite number of solutions. Because of their nature, they will both do the exact same thing and make this single line. I'll just draw it as a single line. I'm pooped. So let's do it. And there it is. That one as well as the green are both the exact same. That means an infinite number of solutions. Yeah, they definitely buried those at the end. So if you keep in mind, if they cross at one point, you got to identify what that single point is. I did that in the very first problems there. Like these ones, negative 3, 6, and 4. If they never intersect, you say no solution. And if they intersect everywhere, you say infinite number of solutions. All right, so that ought to do it for these problems right here. This is solving systems by graphing, and as you double check these, of course, you're seeing a little bit of what it means to work them in with equations. Coming into the next videos here that we're going to be doing ones with solving by substitution. It's going to be called solving by substitution. Make sure you know your distribution. know your fractions. Make sure you know how fractions work with it as well. Know your negatives. And then solving by elimination would be a future one I'll be doing. All right, so that'll do it for me. My name is Mr. Robinson. Take care.